Howdy, campers. All right. We appear to have a major defection among the class. I graded everything that was submitted on time, and it didn't take me very long because not very many people submitted. So that's not good. So submit your assignment. I'll give you partial credit for turning it in late, but you will lose points for turning it in late. Okay, on to Module 6. So we will move away for now from regression analysis, and we will move into simulation. So this is part 1 of simulation. Once I've recorded this video and uploaded it to YouTube, I'll post it here. So this is, the underlying fundamentals of simulation are the rules of probability. And probability is really a separate topic that's worthy of its own course. I took an entire course on probability in college, and I can't summarize all of probability theory in a 1 week module. So you're going to have to, you'll have to study probability another time. But we're going to utilize probability so that you can understand how to use simulation in a decision process, which is the more applicable way to go. So, simulation means that you replicate some sort of random phenomenon, some sort of process that can be randomized, and you use typically some sort of computer program, and in this case, we'll use Excel to randomize. Actually, I'll use Sheets for this, and you can use Excel or Sheets, doesn't matter to me. But we will randomize a couple of simple processes. And, the thing about random processes is that typically they are nearly impossible to predict short term, and they are relatively easy to predict over many, many, many iterations. What do I mean by that? Let's take a coin flip, for example. Can you predict with better than 50% accuracy whether a coin flip will end up heads or tails? No, nobody can unless it's not a fair coin. And so it's not very predictable what the next flip of the coin will be. However, can you predict the probability of flipping heads? How many times you'll flip heads if you flip a coin 100 times? Yeah, that's pretty easy, right? There's a 50% chance that you'll flip heads. And so if you guess 50, you'll be pretty close. 50 out of 100 will be heads. It might be as low as 40, it might be as high as 60, but it's going to be pretty close to 50. So that's the simplest example of what I'm talking about here. And the cool thing about simulation is once you get the hang of it, and once you understand a little bit about how to automate, and we won't do that this week, but we'll do that next week, you can really, create a powerful tool for decision making. Okay, but we have to start small, all right? So by starting small, we're going to start with the coin toss simulation, okay? So you'll click on this link. It'll open up this file. This is a coin toss simulation. Okay, so let me explain what's going on here. So first, I decided I'll just do 32 coin tosses here. And then, so this is nothing. This is just a count from 1 to 32, okay? And then I need to simulate the toss itself, the decision of whether the coin comes up heads or comes up tails. And I use this function right here, rand between, and with the parameters 0 and 1. So just two options. It's either going to be 0 or 1. It's kind of like a light switch, like the dummy variables that we worked on last time, to simulate the toss of a coin. Now, if it comes up as a 1, we're going to call that heads. If it comes up as a 0, we're going to call it tails, okay? And now, so in column C, I'm just simply counting whether or not it's heads. And this is an unnecessary step, but you know, I wanted to be sure that you understood that the random number and its designation are two separate things. Another way you could do this would be to use a random number. A random number is like this, right? So this is a random number. This will return, if I turn on the decimal precision, you can see that it's generated a number between 0 and 1. And if I wanted to use that approach, then I'd have to say, well, if this value is greater than 0.5, then we'll call it a 1. Otherwise, we'll call it a 0. Okay, so it's kind of like the dummy variable setup as well. So you don't have to do it this way. You can do it this way. And notice that every time I press enter and reset, as I reset some things, it will, let's see, maybe not every time. Every time you enter something and press, it should, there we go. It will reset frequently. And you can see that the chart resets with it because the chart is tied to these data. And so every time that you do something different here, and I'm just going to drag this back like that, and I'm going to drag this back too, like that, you can see that every time it starts. Now, and you also notice that with only 32 flips, it's converging on 50% of the time. You're ending up with heads instead of tails. But sometimes you get different sorts of results. So, you know, when you do it a number of times, you know, you might find once in a while, you might find a really low percentage or a really high percentage of heads. However, if you do it lots of times, for example, if we did, instead of 32, if we did 500, we're almost sure to be within a very small margin away from 0.50. We'll get very, very close to it after lots and lots of iterations. Okay, and then, so right here, this is a cumulative count of the number of heads flipped, right? So here is, first it's just looking at C2, then it's looking at C3, is there a new one or not? And it's adding it's adding D2. So D2 is right up here, right? And the first flip, we got heads, so that's 1. The second flip, we did not get heads, we got tails, and so it's still 1, right? We've only flipped heads once. And on the third one, we got tails. So we still have only 1 heads. On the fourth one, still tails, so still only 1 heads. In the fifth, we finally got another heads, and so now we have two heads. Okay, so hopefully you understand how that works. It's just adding the previous number with the whether or not it's a 1 or a 0 here in the C column. Hopefully that's pretty straightforward. Now, column E is calculating the proportion of heads, and that's what's being charted here on this line chart. So it's looking at the coin toss count here, the number in column A, and it's looking at the percentage achieved in terms of the proportion of coin flips that end up as heads. It's looking at that here in column E. And you can see here, it's looking at column E, and then the x-axis is looking at column A, in case you're curious, okay? So you can see that the proportion, you know, kind of wiggles around and then settles, you know, close to 0.5 eventually. But with only 32, it doesn't always get there. But what I want you to do is replicate this, right? So you'll make a copy or you'll download to Excel and see if you can do it in Excel. I haven't tried this in Excel, so I assume this will work, but I'm not certain. The graph may be a little different, so somebody let me know how it goes. And then just replicate this, but your assignment is, instead of 32, do 200 coin tosses and still make this chart, right? So you should converge closer to 50% after 200 tosses, and you'll have to, drag some stuff down and play around a little bit. I want you to, just become familiar with it as sort of the baseline. This is the simplest simulation that I can think of to get you started, okay? So this shouldn't be difficult, but try to understand what's going on here in each of these columns and try to understand the formulas, and then be sure that you're able to get your chart hooked up to the proportion so that you can have a chart that looks kind of like this, okay? All right, that's the easy part. The next part is dice rolling. So if we use this same randomization process, or this function, this rand between, we can also simulate rolling dice, right? So let's look at this dice simulation. All right, this is the easiest possible game. This is called Lucky 7. And basically, you roll a pair of dice, so just 2 dice. Here's die 1, and here's die 2. You roll 2 of them. If you roll a 7, so that the 2 numbers, the 2 die, add up to 7, which is the most common roll, then you are a winner. You win money on that deal. If you roll anything else but a 7, you lose. Okay, so let me walk you through all the columns that I have here. And again, this is a very simple one to try to get you started. Okay, so again, these are the number of rolls, and again, I have 32. And then for the first die, and you have to do these separately. You can't, some of you will be tempted to save time and say, oh, well, let's just do a rand between 1 and 12. To test and see who's paying attention, if you answer, why you can't do that correctly in a discussion, and if it's posted this on a weekday, so before, let's say before Friday, so it has to be posted by Thursday at 11:59 p.m. If you have that, if you're the first one, then you'll get something good. You'll get my undying devotion, praise, and maybe you'll get some help with a score. Okay. All right. So you have to do them separate, and then you add them together, just like you would in your mind when you're looking at the pair of dice that you rolled on the when you see it on the table or wherever you rolled it, and you see a 3 and a 4, then you know that's a 7, and then in this game you'd know that you won. Okay, here in column E, I have the roll result, which is just writing out winner or loser, and this is superfluous. This isn't really necessary or all that helpful, but it shows you the distribution, right? It shows you that most of the time you're losing, and sometimes you win. And when you win, you get a payoff that's better than if you were, if it's better than 1-to-1. So if you bet $5, which is what I have here, but you can change this if you'd like. And if you start with $100, you bet $5, you're losing $5 every time. Finally, you get here and you win $25. Why do you win $25? You bet 5 and you won $25. That's 5 times the amount you bet. And that's what this payoff odds cell is doing for you. It's multiplying your bet and giving you those odds and increasing your winnings by that factor, okay? So for some of you, this is like, oh yeah, I got it, right? Because you, maybe you play poker, or maybe you've gambled somehow before, you like playing games that involve these types of things, or you're into sports, and so you understand odds in some sort of intuitive way. For some of you, maybe it won't make sense at all, but just think of this as a multiplier, right? So the lower this number is, the lower your payoff is. Just think of it as you multiply by your bet, And then if you win, you get this times this. And you can change these around. Now what's going on here is it's at the end, it's looking at your final balance after the last roll. In this case here, it's $90. You started with $100 right here, and you could modify this too if you'd like. And it's just finding the difference so that the house in this scenario won $10, right? Or the player lost $10. But every time I change something in here, like, so if I want to change the payoff odds from 5 to 6, so now a win is worth $30 if you're betting 5. If you bet more or less, it changes. You multiply those two. So when I pressed enter there, you can see that it reset all these randomizations. It reset this ran between 1 and 6, and I got new rolls and a new set of outcomes. And this one's really bad. This one, there was only one winning roll out of 32 rolls. That's really bad. And so the house, so we went into negative territory here because we lost every bet except for this one. And here we got the $30. We had 60 after the last roll, and then we won $30, so we were up to 90. And then we lost, and just kept on losing. And then we put the rest on our credit card, something like that. Okay. So this, here's the total in column D. Very simple. Here's the roll result. Again, this isn't necessary, but it's showing you the logic. If it's 7, it's a win, and if it's not, it's a lose. Simple. And then in column G, we have our beginning balance, and in column H, we have the ending balance. Right? And so we are using the winner here, but you could also look, instead of E2 equals winner, you could do D2 equals 7 if you wanted, and you'd get the same. You should get the same results then. And what's it doing? If you win, it's looking at G2, so that's the beginning balance. It's adding K2 multiplied by J2. So it's multiplying these two numbers, and it's giving you your original bet plus the payoff. So the payoff is the bet times the odds that you put in here, $30. And so if you start with 100, and if you win, if your first roll is a good one, then you'd get $30, and your ending balance would be $130. Okay, so that's the if true part of this if statement. If it's true that you have a winning roll, then you get 130. If not, then you get G2 minus J2, which is the beginning balance minus the bet. So you lose your bet. If you lose the amount that you bet. Very simple. If you win the bet amount multiplied by the payoff odds. Okay, hopefully that's not too complicated. Again, for some of you, it'll be a piece of cake. For some of you, maybe you'll have to scratch your head for a while. But if you play around a little bit, you should get the hang of it. Okay? All right, so the beginning balance here, all you're doing after the first one, and this is, there's no formula here. You can just enter whatever number you want. So if you want to make it 1,000, if you want to make it 500, doesn't matter to me. Make it whatever you want to play around if you like. And then this next, after that, it's always looking, I'll double click on it. It's always looking at the previous ending balance, right? So if we're looking at our second one, the beginning balance is what you had left over at the end of the first round. So you lost $5 in the first roll, and now you got 95, okay? And down here, same thing. At the end of the previous roll, you won some money, so you went from 60 to 90, and so now you're starting with $90. Hopefully that makes sense. And then in the ending balance, this is where the calculation takes place and relies on whether you had a winning roll or a losing roll, and chooses the amount, how to calculate the amount based on that. If it's a win, this is how you calculate the amount. If it's a loss, this is how you calculate the amount. Okay? Make sense? And then this last one, this house take, it just subtracts the beginning balance by this last ending balance. And that becomes the house take. And the house take could be negative. So if there were a lot of winners rolls here, then the house take might be negative. So the ending balance might be like $150. If you won $50, then the house take would be negative 50. Let's try a couple. Let me go back to 5. Oh, another terrible one. There we go. There's a few more, but now the payoff odds are only 4 to 1. So when you win, like here, you only get $20 because the payoff odds went down. If we take them back up to 6, it'll reset. And this time there are a few wins. You can see that the ending balance is 185. So this was a good one for this player. Won how many times? 1, 2, 3, 4, 5, 6, 7 times, and 3 in a row here after 2 in a row. And so what you got there is a house take of $85. The house lost $85 because the player won $85. Okay, so this simulates the simplest dice game imaginable, Lucky 7. You could come up with something else that's probably as simple, but I can't imagine anything simpler than this. Okay, now, so hopefully you're understanding what the very basic building blocks of simulation. And we're just focused on what's called discrete probability, right? And so the options here are only integers, excuse me. You can only have an integer when you use this rand between function. See this uniformly random integer between 2 values. Another type of randomization or another type of random process is continuous. And for that, you would use the other function that I showed you a little earlier in the video, and that's just this rand. And it pulls any random number between 0 and 1. And so it can be, you can then represent a continuous distribution using that function. But you don't have to worry about that this week. We're going to do something like that next week, okay? All right, so in addition to, so you'll replicate the coin toss simulation. You'll do 200 tosses instead of the 32 that I have here. And then your graphic will show an x-axis that's 200 tosses in width here, and this will look the same. This might move around a little bit. Don't worry about it. In order to have the flexibility of it changing every time this changes, I think you might have to give up control over the y-axis a little bit. I played around for a while trying to make it stick at between 0 and 100. Maybe I did, but I can't remember. But sometimes this will move around. Don't worry about it. It's okay. So you'll do the coin toss. You'll simulate Lucky 7. You'll replicate that, and then instead of 32, you'll roll the dice 100 times. So there'll be 100 rolls here, and so you may need to change these numbers, the beginning balance and the bet, to accommodate the 100 rolls that you'll have here. And you can leave the rest of it the same, or you can make it your own and change things around if you prefer. You probably can figure out how to use color and all kinds of stuff, okay? That's not part of the assignment, it's not required, but if you want to have fun with it, go to town. Okay, and then the challenge part of this week's module is to simulate another simple game. This one's called Chuck-a-Luck. It's kind of a weird name, but it's very simple. If you click on here, you'll go to this Wikipedia page that describes Chuck-a-Luck. And it's an old game. It's also known as Birdcage, apparently. And basically, you roll 3 dice. And then there are a handful of different ways to bet. And you can read about those here. But I only want you to simulate 2 different bets, only 2, okay? And so that this could be pretty complicated if I wanted you to simulate all these different options and you had to decide on a bet, or multiple bets or whatever. We're just going to assume that there's always one bet, and whoever the player is, the player rolling the dice, they're the one who is making the bet, and they're the one who benefits if they win the bet, and they're the ones who lose money if they lose the bet, right? So here are the rules. It's the same page, but just links to the rules section. Basically, it's you roll the 3 dice, and then you add them up. And if you get a sum greater than 10, and that's not greater than or equal to, it's greater than. So it has to be 11 or better. Then you win what they call the big bet. And so that means that you had a big roll, right? And so if you bet $5, the odds here are 1 to 1. The multiplier is just 1. So if you bet $5 and you win the big, you get $5, right? So if you started with $100, you bet $5 and you win your first time out, now your ending balance is $110. So I'm sorry, it's $105. You won $5, right? And so it's not a huge payoff the way the Lucky 7 was. It's a very modest payoff, just 1 to 1, which is probably the typical type of bet that you would engage in. However, we're going to also reward the player for any triple. So if you roll 3 1s, 3 2s, 3 3s, 3 4s, 3 5s, or 3 6s, so whatever, the dice all come up the same number, that's a triple. And if you roll a triple, the player gets paid out 30 to 1. So if you bet $10, multiply by 30, that's a $300 payoff. Pretty good, right? But it's rare. And so those are the only 2 winning possibilities for the player in your Chuck-a-Luck simulation. Those are the only 2 rules that you need to program up, okay, or code up inside the spreadsheet. Any other outcome. So if the player does not roll 3 of a kind, and if the 3 dice sum together have a value 10 or less, then the player loses the bet. Okay, so it'll look like this, right? You can set it up like this, except for you'll have to have a 3rd die here. You'll have to do the total, and then you'll have to check to see if it's a triple or not. And then you'll decide what the payoff is, okay? And you're going to have questions. You'll be like, oh, but what happens if this? You decide, okay? You get to decide. So maybe if there's some exception that you're not thinking about now, but once you get in there and then you realize that there's something weird going on when some particular set of some roll pops up and you aren't sure how to handle it, you have to make a decision and handle it, okay? And then I want you to play around enough to try to answer this question. Will the house win money over time with these rules? Simple question, right? Because this is a pretty big payoff. 30 to 1 is pretty big time. You can hit a few of those and, you can lose a lot of bets in between and still come out ahead. And this is just a very modest payout, 1 to 1, if you get 3 dice adding to 11 or higher. So, will the house win money over time? I don't know the answer. I want you to find the answer. And I want you to explain how you arrived at it, right? So maybe don't just say yes, the house will win money, or no, the house won't win money. Explain your thinking process, and you might experiment once you've built your simulation. Maybe you experiment a little bit, and you can have what's called some empirical data. You can bring it to bear, right? So these are tests and results, and you see. So maybe you play the game with 100 rolls 20 times or 30 times, and you record the outcome, how much the house took each of those 30 times. That's evidence to support your hypothesis that the house will win money, right? Okay, so this is how we use a simulation. Next week, we'll do a simulation of continuous probability. It'll be with the stock market, and we'll also do some automation. And I think you'll like it. In the past, it's been a popular assignment, so I think you'll have fun with it. And it'll show you the potential ups and downs of letting Wall Street pay for your future retirement or not, right? So if you have questions about this, get on that discussion board. And I don't know where you guys are. I've sent out some announcements. You have to participate in the discussion board. If you don't, you'll have zeros on all the, here's where I made the announcement. Discussion boards are a ghost town. You are aware you're graded on the contribution of discussion boards every week, right? It's 20 points every week out of a total of points for this course of 1,000. Your assignments are worth 80 each week. And so if you're not doing anything, you're going to struggle. You're going to have a hard time passing the class. So, you know, it doesn't take very long to post something into discussion. Do it. It doesn't take that much discipline to turn in your assignment on time, which is Sunday night. Last night, you should have turned in the Module 5 assignment. Do that too, okay? And if you're not sure what to do, you can email me or you can post a question on the discussion board. That's the idea. Okay, but right now, a lot of people aren't participating and I'm worried about the grade. I'm very flexible and I'll take late work, but at some point, if you're not doing anything, it's going to become difficult for you to pass the course. So start stepping up, okay? All right, so I'm going to post this video. I'll post it right here. And hopefully, and you can download these, right? So you'll be able to get your own copies of these and utilize them. And then you'll have to figure out Chuck-a-Luck and how to simulate it. And you'll be able to use these simplifying assumptions. And for some of you, it might feel really hard, but it's definitely doable. You can get in there and do it, okay? And if you get in there and you're not sure what to do, make some additional simplifying assumptions if you need to in order to get something done that you can submit on time, all right? And, you know, again, email me, post discussion board. I'll be happy to answer any questions. But hopefully this gives you enough information to simulate Chuck-a-Luck and find out if it's going to be a winner for the house or not. Okay? All right, guys. Have fun with Simulation 1. And I'll come back to you next week with Simulation 2. Have a good one. Meeting controls. Stop video. Oops. Stop share. Bye-bye.